Next, I would like to explain a binomial array as another array synthesis method. For the beam pattern, suppose that the array factor has the following form. F of u equals exponential ju over 2 plus exponential minus ju over 2, all raised to the power 2n. Using Euler's formula, the term inside the parentheses becomes 2 cosine u over 2. Therefore, the array factor can also be written as 2 to the power of 2n times cosine to the power of 2n of u over 2. The maximum value of the array factor is 2 to the power of 2n. Now let us think about the shape of this pattern. At u equals 0, the cosine takes its maximum value, so the array factor also reaches its maximum there. Because the argument of cosine is u over 2, the pattern becomes 0 at u equals plus or minus pi. As the cosine term is raised to a higher power, the pattern drops very quickly, and the transition becomes steeper. Because the expression is raised to the power 2n, we can apply the binomial expansion. If you have forgotten the binomial theorem, I will also show it on the slide. The binomial coefficients can be obtained by Pascal's triangle shown in this diagram. Each number is obtained by adding the two numbers directly above it. These numbers are the binomial coefficients that appear in binomial expansions. When we expand the expression, we obtain a summation with binomial coefficients. Then, by combining the exponential terms and by changing the summation index so that it runs from minus n to n, the array factor becomes a sum of exponential jmu. The coefficient of each term is the binomial coefficient. This means that the pattern can be realized by a linear array with two n plus 1 elements arranged on the z-axis. The amplitude of each element is proportional to the corresponding binomial coefficient. This kind of array factor has an important advantage. It has a single main lobe and no side lobes. That means unnecessary radiation is not sent in unwanted directions. However, there is also a drawback. The main beam becomes wider. So in this design, there is a trade-off between side lobe suppression and beam width. Now let us plot the binomial array. First, we define the function in GNU-plot. For the array factor, we use n as a variable. Instead of writing out all the coefficients, we use only its shape. We write it as cosine u over 2 to the 2n with the maximum amplitude normalized to 1. This gives a binomial array with 2n plus 1 elements. Then we set the number of sample points higher. First, let us consider a 3-element array. We set n equals 1. Then 2n plus 1 becomes 3. The plot looks like this. This shows the kind of array pattern we can obtain. This point is minus pi, and this point is pi. If the element spacing is lambda over 2, this point corresponds to the plus z direction, this point to the minus z direction, and this point to pi over 2. Now let us see what happens when we increase the number of elements. We increase it a little, and this is a 7-element array. Then we increase it by 2 more. Now this is an 11-element array. Next, let us show the radiation pattern as a polar plot. The dummy variable is t. However, this expression is still a function of u. Here, u equals pi cosine theta. To rotate the plot by 90 degrees, we write it in the form subtracted from pi over 2. We do the same here as well. If we set it up in this way, we obtain this pattern. This is the 3-element array. This is the 7-element array, and this is the 11-element array. There are no side lobes at all, but the main lobe is somewhat wide. So this is an array pattern in which only a single main lobe appears.